Hello again, everybody. Welcome back to another exciting evening of physics. Today, we're going to talk about throwing things in the air, whether it's your cat or your little brother or whatever you do. In general, we call any of those things that are flying in the air without wings projectiles. So anything that's projected or kicked or thrown with an arm. So planes don't count and birds don't count, but everything else we're going to lump all together. Projectiles have kind of a cool history. It used to be thought that when you shot something out of a cannon, you gave it some sort of its own fuel almost, and it would go up, and when that fuel ran out, it would fall straight down. Now, this picture is not one of the cannonball hitting the side of the picture, but it running out of whatever this stuff was that it had, and then it would fall straight down. So the reason we know this is people wrote about it and drew pictures like this. Here's another one where if you look, the ball coming out of the cannon, no matter what angle it's shot at, goes straight for a while. Then it curves, then it goes straight again. So again, maybe we've added a little bit of sophistication with the curve, but we're still kind of off. That's not really what things happen. Here's another one, a little bit closer. You can see this one kind of curves at the top, at the front end, but then when it lands, maybe not quite right. Well, Galileo was the dude who just nailed this right on the head and got it right for the first time. This is what we've been talking about in class a little bit, but this is a picture from his notebook, one of his notebooks, and it shows these curves, these parabolas, and he figured out that the curves that things fly in are parabolas. But this is one of the pictures that we've looked at from his notebooks, or stolen, if you will, to kind of figure out what's going on. And we pretty much know he was the man. So let's look at projectiles, but let's have a special case first. And we've been dealing with this for a little while with our labs, which is we're going to launch them horizontally. Okay? And we talked about launching them horizontally and dropping something at the same time. And we found that they drop at the same speed as they fall towards the ground. So let's try something here. I'm gonna add a few things to my drawing here. I'm gonna put a dotted line right across here at each of these spots. Maybe this is 1/10 of a second or a 1/2 a second or something like that. So if I were to take this marble and drop it like this from the top of the table, and I took a strobe picture maybe every 1/4 second or something. All right, that's the marble falling to the ground. Now, if I were to take that same marble and shoot it horizontally out, what I'd get, I'm going to just draw some dots. All right, so I've got a solid marble now. If I took my flash pictures at exactly the same times, what I would get is this marble falling exactly the same distance down as the one that I just dropped. And this is one of the things that we did in class. All right? So big idea. Galileo figured out it doesn't matter how fast I shoot it. The falling part is always the same. And he figured out something else. If you check the lines in between where these are in the horizontal direction, check this out. They are equal. Now, if I'd drawn a little better, in the acrossways direction, we're not speeding up or slowing down. All right? That's huge. That's a ginormous thing. So I have a question for you. If you were to go to the end of this board and look at it from the edge, what would you see? Well, you'd see these marbles falling. I'm trying to make them fall straight. Falling straight down. But if you were far enough away and we dropped one and shot one at exactly the same time, you would see them drop together. One would be immediately behind the other one. As a matter of fact, you couldn't even see the one behind. They're falling perfectly in line so well. So here's the big idea for this thing we've been talking about. The across motion, the horizontal motion, and the up and down motion, or the vertical motion, are totally separate from each other. One does not affect the other. They don't even know about each other. Okay? So that's a huge idea. So again, I'm going to tell you over and over, let this sit inside your head for a little while and become kind of a stew, all right? So sorry about that. I jumped to the wrong picture. We're going to do something now. We're going to make the next step up to shooting things up now, or shooting them down. We're going to start with up. All right? So now instead of launching something horizontally, we're going to launch it up. And what we're going to do with math is we're going to use the same trick we used when we divided up gravity into two components. Okay? Now, for this one, we're not going to divide up gravity, so don't get started too much. We're going to divide up the velocity. So I'm going to shoot a cannonball or a cat or something with a certain velocity. V0. Okay? Now, if I shoot it at some angle, and we'll call the angle theta, I want to find the up and down part of that motion and the acrossways part of that motion. So, the acrossways part is going to be the vector like that, and that's going to be V0 in the x direction. Whoops, there we go. And then we have part of that velocity in the y direction, and that's going to be here. And that's V0 in the y direction. Okay, and if we could move V0y over to here if we wanted, and we could move V0x up if we wanted as well. Okay, so there's our kind of triangles and boxes. All right, now check this out. Let's talk about just the up and down motion. So if I were to take a marble and just launch it up and down vertically, okay? So if I launched it with V0y, so I'm going to launch it with this velocity straight up in the air, okay? So if I take a marble and I launch it straight up with V0y, it's going to go straight up and come back down. But here's the crazy thing. It's going to come back down with exactly the same amount of time as the one I launched with V0. Okay? Now, let's have a look at that and we'll see if we can figure it out. So, I've drawn something here. I've drawn the up and down motion of a particle being launched straight up in the air. Okay? Now I drew the marbles on the going up and down next to each other so you could kind of differentiate them, but it would go up and it would come back down in exactly the same spot. Now here's the crazy thing. If we launch something with the same vertical velocity, gravity is going to act on the up and down part of that motion exactly the same. So let's put some of those dotted lines on here again. All right? Let's say we launch it and we take a picture, like, I don't know, 1/10 of a second later. as that ball's going up, they're both at the same height because gravity is slowing them down exactly the same. All right? At maybe 2/10 of a second later, again, they're at exactly the same height. 3/10 of a second, they're slowing down, but they're slowing down exactly the same. All right? 4/10 of a second, and let's say this is half a second later. So this thing went up for half of a second. Now it starts coming back down. All right? And as it comes down, they both come down the same. As gravity starts to accelerate them towards the ground again, they come down at exactly the same speed. Here's the difference. Notice, after 1/10 of a second, the ball that is launched at an angle is that far away from where we started. 2/10 of a second, 3/10 of a second, 4/10 of a second, 5/10 of a second, a half of a second. It's at the top, as is the one I launched straight up, but all it's done is moved over a ways. And then as the marble comes down, it lands at the ground over there. Notice something. In the across direction, the speed never changed. There's no gravity to speed it up or slow it down. It's just going to keep cruising right along. The up and down part doesn't know what the acrossways part is doing, and vice versa. They don't care. So, again, if we looked at it from the edge, we would see the balls go up and then come back down, but one would be immediately behind or exactly behind the other one. All right? Now, you guys, this is a tough idea. So sit with this for a minute. The acrossways motion and the up and down motion are not connected. All right? So what would we see from the end? We talked about that. Now, here's the deal. Galileo, he's definitely the man. I mean, he actually figured this out. So we can read his books and write it. Now, if you were somebody that figured this out, you might look kind of goofy like this. He has something like a sideways mohawk or something going on, and he's got the weird eye thing. I don't know. Definitely not somebody I'd want to hang around with a lot. But the coolest part, I think, about Galileo was after he died, and this is 100% documented, someone took the middle finger of his right hand and cut it off. And a bunch of people watched it and signed papers that they did this. And they dried it up, and I don't know what they did to it, but it's in a glass. And you don't drink out of it, but it's just for display purposes only. And it's in a museum in Florence, which is just kind of crazy and creepy. I think it kind of goes along a little bit with his general looks and vibe when he was alive. So anyway, there's your video problem, and I hope you enjoy.